I hope you understand that. In a perfect world, I would be able to give you a solution. Okay, we are going to start something new today. This is a new chapter, a new topic, just basically new. Here it is. We are now looking at how do you integrate multi-dimensional functions. And we are going to focus on double integrals. But in this chapter, you will do double and triple integrals. And what you have here is my very badly drawn, and then I had another try and it was just as bad, of trying to show you what you are getting geometrically when you calculate a double integral over a rectangular region. So when you imagine that you've got, when you imagine you've got your surface, right? Your curved hill, z equals f of xy. And below it on the xy plane, there's a rectangular region typically called R. So this rectangular region, you go upwards like a cuboid, right? And then you hit the surface. And when you hit the surface, can you imagine that the net effect would be you might get a shape that looks something like this. And the volume of this solid shape is what you are calculating when you get a double integral over a rectangular region. So can you imagine that this is what that shape would look like? Now, it's not a cuboid. And the reason it's not a cuboid is the top typically is not a flat roof. Isn't the top the surface that Z would be over that particular rectangle? And that surface could be indented. So you can imagine it's like a cuboid and then somebody scooped some ice cream at the top or whatever, and it had a kind of dimple in it, right? But that's what we are going to be calculating. So some notation, because there's various versions of the notation. Sometimes they write it one way, sometimes they write it another. Here is the generic version of a double integral. So out loud, you would say double integral of the function xy dA. dA is a general description. You're doing the derivative over an area, a region if you prefer. And in this case, the region happens to be a rectangle, but that region could be, could you imagine you had a circle on the floor and you went upwards? Couldn't you get an area under a circle? And couldn't you get an area under a triangle, not just a rectangle? And so to be more generic, we say dA. So dA is some region on the ground that you project upwards and you make the surface Z there. Now, what could happen if the surface Z wasn't above the XY plane, but it was below the ZY plane, right? Surfaces can have negative Z values, right? What do you think might be the result in this double integral? It's still a volume, right? But negative. Now, the analogy would be, can you remember Calc 2, the area above a curve could be positive, but couldn't you do the area below the curve and it could be negative, right? So this is allowable. So when you do calculations and you do a double integral, we haven't looked at how you do that yet, but you will do it. The answer will be 42, but it could be negative 42, right? And it could actually be 0. Because couldn't you get a shape where half of it was above the XY plane and the other half of that solid shape was below? And couldn't the bit above cancel out the bit below, right? I mean, I could just imagine all sorts of, surfaces that would generate that. So just like in Calc 2, and a single integral could be positive, negative, or 0. In this world, in the two-dimensional XY world, you can get positive, negative, and 0 for that. Now, this version here is the specific version that you use when it's a rectangular plane. So I want you to imagine the x's go from A to B, and the y's go from C to D. And typically, you won't find textbooks put the y equals C, y equals D bit in, or the x equals A, x equals B. But I put that in because I forget who's who if I'm not careful. And so if I say y equals 2 and y equals 3, I know that's the y values. And then x equals 1 and x equals 7, I know that's the x value. So that's for me, but I think it's helpful. Now, have you noticed that the dA has now been converted into a dy dx? Isn't that beginning to look a lot more like-ish Calc 2 integrals? But the difference is you don't integrate with respect to one variable, dx, but you integrate with respect to two variables. So, suppose I said I would like you to do the double integral from 0 to 1 and from 2 to 3 of x squared y dy dx. So in this case, you don't need to worry about what everything is because this is given to you on a plate, right? All the things are in the right place. This really means y equals 2, y equals 3, and this means x equals 0, x equals 1. And you may say, how do you know that the y's are 2 and 3 and the x's are 0 and 1? It comes from here. You're doing y first, so the limits of integration are y. As you move out, you do x next, so the limits of integration are x's. Now I'm going to rewrite this guy again in the typical way I would write it. You can choose to or not your guy. Okay, here's your first problem. If the world was nice and math had structure, how do you think you would integrate x squared y dy from y equals 2 to y equals 3? You've never seen it, but how would you expect that to happen?
It's going to be 1/2 x squared y squared, right? This is sort of like partial derivatives.
Correct.
Where when we took the partial derivative of y, x was a constant, and now since we're taking the integral of y, x is regarded as our constant.
You nailed it. In fact, I think you said it better than I was going to say it, so I'm not going to say any more. Exactly what she said. Does that kind of make sense that you would integrate with more than one variable, like a partial integration thing, right? Now, you would then evaluate it at y equals 2 to y equals 3. Stick a big box around that. And then you do the integral. You basically leave this. Right, so let's see what I get when I start plugging in some numbers here. It's going to be the integral from 0 to 1. If you plug in 3, you get 1/2 x squared times 3 squared. Take away 1/2 x squared times 2 squared dx. And that becomes integral of 1. That becomes 9/2 x squared. And I believe that becomes 2x squared. I'm not quite sure how many of these lines you truly need. But that guy, take away that guy, I believe leaves me with 5/2 x squared dx. Now, normally when there's only one variable left, I might not put x equals 0, x equals 1 here. But here's something I think it's interesting to me. Isn't that a Calc 2 question?
Pretty much.
Isn't it just a normal dx that you would have learned how to do? Now, add 1 to the power, so it's a power rule. Divide by the new power. Evaluate at x equals 0 to x equals 1. And I can do that in my head. Would you agree the answer's 5, 6?
Yeah, I agree.
Great. So are we happy with double integrals, at least the first one we've seen? It isn't too weird. Would you agree? It's really just a matter of partial integration. And you just keep your order. Make sure you know who you're doing first, in this case, y. I want to show you some interest, I think, again, some more interesting properties, and I'm using this guy. If you switch the order of integration, in other words, do the x's first and the y's second, as long as you make sure that the limits of integration also follow the variable. So you notice how the 0, 1, and 2, 3 have now become 2, 3, and 0, 1. And you know how the y first and x second has now become x first and y second. Do you know that both of those get you the same answer? Does that seem a reasonable thing that you would have expected? Now, the calculations and the algebra might not look the same because of what you do first and what you're doing second, but the final answer will still be 5, 6. Oops, someone. So far, so good. Okay. Now, sometimes, but not always, you're allowed to do this. If this expression here, if it is separable, you know, like variable separable in differential equations, if they are distinct something with only x's times something that only contains y's, if you can do that, you can actually split this double integral into the limits with x's and the x guy, and the limits with the y's and the y guys. Now we know the answer to this question is 1/3, so let's see if that happens. So this is 1/3 x cubed evaluated at x equals 0 to x equals 1. And this will be what? 1/2 y squared evaluated at y equals 2, y equals 3. You plug this guy in, you get a third, take away 0, so you get a third. You plug this guy in and you get 9/2, take away 2. So you'll get 1/3 times 5/2 altogether. And guess what? So the process of evaluating a double integral can simply just be as we did here. Do the y's first, plug in the answer, do the x second. You can choose to switch the order. Right? You can do the x's before the y's if you feel like it. And if you're really, really lucky, you can actually take it and split it into 2 single integrals. You cannot do it for a lot of situations, but the few times that you do it, I think it's worth it. And can you imagine I had an integral like this? It ain't going to happen, right? You'll never split that. So you wouldn't be able to do this, right? On the other hand, this could be split. And it would be split like that. Great. Now you may think, oh, well, why bother? The why bother is because you know that these can be very time consuming, especially if these expressions are really messy. And anything that makes your life easier is worth it. Typically, splitting something into two smaller integrals tends to be less work than doing it the long way, right? Doing this. Why do you think switching the order might sometimes make your life easier?
Sometimes it's easier to do your integral with respect to one variable first. Like if we had something like e to the x and we integrated with respect to y first, then actually, now that I think about it, I'm not sure that that's the best example.
That's not a good example, but the idea you're expressing is a good reason. There are some situations where doing the y first would be a real pain in the butt. But if you do x first, and then especially if x is 0 and 1, a lot of things disappear on you, and the next integral is a lot nicer than it would have been. So for calculation purposes, it can be useful. Analogy. Do you know sometimes when you're doing a partial derivative, like a double partial derivative, isn't it sometimes easier to get the x before the y than the y before the x? You know, because sometimes they end up nicer looking or less work at least. So it is possible, right? It may happen that most of the time it makes no difference. It's just as much work one way as the other. Which case, okay, do whatever order you feel like. I do think splitting, however, if it's possible, is pretty much guaranteed to give you less work. Now, before we actually start doing any more of these guys, try to find my clock because I'm watching, okay. Let me remind you of Calc 2 techniques. So you are going to come across integration, and therefore you have to be kind of up to speed on integration. Suppose that was an integration that you had to do. I'm taking the y's out because they're a distraction. What technique will I use to integrate that?
U substitution.
Agreed. What would your U sub be?
ln of x.
Correct. Suppose you're that guy. What technique would we use?
Integration by parts.
Agreed. Now, some people do the UDV version, that's fine. I do the FG of X version. So you would have to make this fellow the F of X and this fellow the G of X if you do the FG version. If you do the UDV, you know, that's the fellow. Now, here are two similar questions. I think they're similar questions anyway. They have powers of x's and they have e to the something. What technique will you use for the top one?
I would personally use U substitution for that. Because
it would be what?
Say again.
What would the U sub be?
My U would be x cubed.
Correct. The one underneath it is not a U sub. Agreed? I mean, it looks, it's got an x in it, and it's got an e to the x, but it is not a U sub. In fact, I could make that x squared if it helps, because that second one would be an integration by parts. So just because an an integral looks very similar to something that you used u sub on doesn't guarantee it. And you know you're going to do power rule, and just off the top of my head, you're likely to want to integrate that guy. Does anybody recognize what the antiderivative of that fella is?
Inverse trig function.
Yeah, I think it was saying it was inverse, Dan. Yep. So you're going, yeah. So I'm assuming that you know how to integrate things, right? So that's something you got to get. If you got a little bit rusty on it, you may want to go and look at standard integrals and maybe practice some techniques. The techniques that you're likely to use are the power rule, u subs, or integration by parts, right? They're the kind of bread and butter techniques. And on top of that, just having a good memory for the standard integrals will do it. So let's try the integral from 1 to 3, the integral from 0 to 1. I'll make it 0 to pi, more interesting. X squared sine y dy dx. Now, just because you may not end up doing it the way I'm about to do it, that's fine. You're going to get the right answer. But is there an efficient way of tackling this question?
It's separable.
Yeah. Now, these two guys belong with the y, and these two guys belong with the x. Are you comfortable with recognizing who the y's are and who the x's are? Because one of the common mistakes is people just forget or don't pay enough attention, and you're doing most of it right, but you're using x interval values with y's and vice versa. Now, if I want to split this guy, the x's are going to go from 1 to 3, right? Which is just an overkill of this guy. And then the integral from 0 to pi of this guy. This fella is 1/3 x cubed. And this guy, okay, what'd you get if you antiderivative of a sine?
Minus cosine.
Correct. Right, this guy gets you 9, take away 1/3 times. Cosine of pi, well, cosine of pi is basically -1. So the negative and -1 is 1. And the cosine is 0 is 1. So you're taking away -1, so you're going to add 1. So you're going to get 2 out of this. And you're going to get, yikes, 26/3. So 52/3, I think it is. You can double check my math in your own time. Okay, let's show you some ways. To me, that's the nicest way to write it, because if they write it down this way, you know everything. But you might get it written like this. Okay, this guy is pretty easy. They've just told me who of f of x, y is. So I'll do my double integrals, and that guy's going to go there. This notation is a little bit less clear, but this is telling me what the x's do, and this is telling me what the y's do. So the convention is from x equals whatever these are, and the y's vary from whatever these are. So if I'm going to do the x's, it would go 0 to 1, which means x is first, and then 0 to 2, which means y second. And if you want to put the little x equals 1s and y equals, feel free to. If you don't need it, then don't bother. This question cannot be separated. Would you agree you can't pull out all the x's times all the y's, right? It's not that. I don't think there's any advantage in switching the order either. Would you agree? It's probably just as ugly one way as it is the other. So I'm pretty much just going to do it as is. So it's going to be from y equals 0 to y equals 2. Okay, let's integrate with respect to x. Well, that's just a typical power rule. And if you integrate e to the xy with respect to x, you get e to the xy. But that's not all you get. Right? It's essentially, it's a chain rule, isn't it? You know, like e to the 2x would get you e to the 2x, but when you also get times a half.
Yeah, so wouldn't you get 1 over y?
Right, and now I'm going to change that question so I don't get a silly answer, right? We're going to evaluate this at x equals 0 to x equals 1. So let's see what happens here. If you plug in 1, you get a quarter. If you plug in 1, you get 1 over y e to the y. Take away, if you plug in 0, you get 0. You plug in 0 here, you basically get 1 over y. And so it's going to be the integral from 1 to 2 of 1 quarter plus 1 over y e to the y. Take away 1 over y dy. And since I made this question up, it's not going to work out quite as well as I wanted. Would you agree that's just a quarter y, and would you agree that's just going to be a natural log of y? I do have a problem with integrating 1 over y e to the y. Would you agree? I got a problem with that.
Yeah, that probably requires integration by
Some weird stuff. Well,
I'm just
no,
confused
yeah.
on how you got the minus
Hmm?
0 plus 1 over y dy.
Here? Oh, okay. Plug in 1. No, sorry. To get this guy, plug in 0. Quarter 0 thingy 0. 1 over y e to the 0 times y, but that's 1 over y e to the 0. E to the 0 is 1, so it's 1 over y.
But
If
how'd you
plug
come up with
0
the
into
minus?
this,
So how'd you come up with? I understand how you got 1/4 over 1 to the y e to the y, but you have minus 0 plus 1 over y.
He's evaluating the
Okay.
integral. So for the first two, that's where it's evaluated at 1. And for the second two, that's where it's evaluated at 0.
Oh, and you subtract the 2.
Yeah. So that's the bit that this is coming from. If you plug in 1, you get this. Take away, you then plug in 0. That's the quarter. That's the ugly 1 over y e to the y. That gets you 0. And e to the 0 is 1. So you get only that. And that's where this came from.
Okay.
Right. Now I'm just going to dot this thing because I'm not even sure that's going to turn out anything vaguely nice. You are not given questions that are impossible. So I will look at the examples in the homework, and that way I won't come up with questions that just don't finish because the expressions are silly. That process was totally fine. If I could have found an integral for 1 over y, e to the y, it would have been complete. Let's see. Oh, this one's good. The integral from 1 to 16, the integral from 1 to 4, x over y plus y over x, and they're asking us to do the y's and then the x's, and you cannot separate that. The minute you see things with pluses and nah, it's just not going to separate. So we're going to do 1 to 16. And this fella here, basically, this guy, is who we do first. So x over y integrated with respect to y. What would x over y get you if you integrate it with respect to y?
Negative x over y. Oh, never mind. I was doing derivative.
Differentiation, but right, keep that thought and then switch it back to integration then. So what would x over y get you if you integrate it?
X ln y.
Yeah, agreed. And if x's throw you, I don't know, call it 42. I like 42. 42 over y, wouldn't that get you 42 log y's? So x over y would just get you x log y. You know, see, just stick a number in, do what you would have done. Make it a nice number like 42 so it won't mix up with other numbers, right? It'll stand out a little bit. And then replace it by x and you're good. Now, y over x with respect to y. I want to integrate that guy. I could call him y over 42, right? Which would be 142 y's, right? Now, isn't that simply a power rule? So you add 1 to the power and you divide by the new power. So what does that look like when you do it to this guy? You add 1 to the power and you divide by the new power. Can you see my 42's by x? And then we evaluate it at x equals 1 and at x equals 4. You plug in 4 here, you get 4 log y.
Wait, this is for dy, I think.
Oops. Thank you. Which tells you why I should write y equals every single time. Because that's what I tend to do. You know my little trick where you label the limits of integration. See, I would be less likely to have made that mistake if I'd said y equals 1 to 4. You see, my brain would have kept the 1s and 4s. So thanks for catching that. It's going to be x times log 4 plus 4 squared over 2x. Subtract, plug in 1 now. X log 1 plus 1 squared over 2x. So it's going to be the integral from 1 to 16. Can't really do anything with that fella. That's 16. 16 over 2 gets me 8 over x. Not really a lot I can do with that guy. Oh, there is. What's the natural log of 1?
0.
Right, so it's nothing at all. And then take away the last guy. Are we good? I have an 8 over x. I want to take away a 1 over 2x. I can tackle this question in 2 ways. The first way is that I could just leave them alone and integrate each one separately. and then figure out, you know, how to make the answer at the end look pretty. Great. Could do it that way. Or I could combine them into a single thing. I don't really think it makes much difference. They're going to be a lot of work. I'm either going to make it look pretty at the start and then integrate, or integrate as it is and make it look pretty at the end. So let's just leave this guy alone. But I'm going to rewrite 1 over 2x as a half of 1 over x. And the reason I want to do it that way is coming up right now. If you integrate x log 4, isn't it just 1/2 x squared log 4? Because log 4 is just a number. Won't 8 over x get me 8 natural log of x's? And if I write it this way, won't this just get me negative 1/2 natural log of x? And then you can evaluate it at 1 and 16. If I had left the question as that, right, I could have just left it as 1 over 2x. What is the antiderivative of 1 over 2x? Well, I guess that answers my question. Since you're not being able to tell me what it is, it's not a standard integral. It's actually technically it's a baby U sub. It would be that guy. Anything else?
Times half.
Times a half. Do you really think that's going to come out well? So calling it a half 1 over x, doesn't it just make the answer much cleaner? Just easy to deal with. So if you ever get a 1 over 5x, 1 over 2x, 1 over 7x, I suggest you do this little trick. It just makes your life easy. Right, I'm going to have to dot this because I don't want to spend time just number crunching. But would you agree you could plug 16 in here and then plug in 1? And it looks to me like you're going to get various combinations of various logs, aren't you? And then could you just add all the logs together? Add's a bad word. Combine all the logs together into one single log so that you've got style points. So this is not the correct answer, but I want you to pretend that you got this. 8 log 4 plus 8 log 2, take away a half a log 2. Imagine that's what you got when you were finished. That is not considered good form. This fella is him. This fella is him. And this fella, actually, let's redo that. Going to just combine them into 15 halves, log 2. Right, 8 take away 1/2 is 7.5, which is 15 halves. And then you could do a single log of this guy over this guy times something like that. And that's actually not as nice as it could be, but it's close enough. Try if you can. What I'm getting at, I guess, is try if you can, if there's lots of logs, to try and put them together as a single log. I'd probably leave it like that. That looks slightly nicer. Let's see if I can find a separable one. No, that's not separable. That's not separable. Oh, okay. This one is. Just a different way in which the question is going to be described to you. Okay, this double integral of this function with respect to a generalized area, and this is the area. X can go from 0 to 3. Y can go -2 to 2. I think that's quite obvious what that's trying to tell us. And I'm doing X and then Y. Maggie, shush. Take your poo walk in a minute. Can you hear her? That's the old girl. Okay, let's look at how we'd approach this question. Obviously, you could just approach it the way you always do, right? Do Y's first, do X second. So there's anything in this question that looks a little bit nicer. Come on, let's go. Come on, let's go. Come on. Come on.
I
I was
would
trying to con her to leave the room. Right, go for it.
I would integrate by y first because it's only in the numerator and the rest is just kind of a constant along for the ride. So we're gonna do like, oh, or I guess you could separate it.
Do you see how this one is separable? Now, what Lindsay was saying would work fine. You get the right answer. And in fact, this one's set up to do the Y's first. Couldn't you switch the order of integration and do the X first? Although I probably wouldn't want to. Would you agree in this question, doing the Y's first is probably less work than doing the X's first? But in this particular question, don't you even get less work, I think, if you split them. Now, this fella is a no-brainer, right? Boom. I don't have time, and I don't want to take away all your fun. How would I integrate the X fella? Come on, Anna, I'm putting you in a spot. Look at X's. What would you do?
Is the x squared plus 1 an inverse tan?
It might be, but the 3x stops you from doing that. Well, it is, but the 3x stops you from doing that.
All right.
I think I've lost Anne. Anne, where are you? Oops. There you are, Anna.
I would do a u substitution with x squared plus 1.
Correct. And you'd end up with, oh, don't quote me on this, but something like 3/2 log u, and then you could replace the u with x squared plus 1. So you end up with some log type stuff. That'll just be some ugly fraction. That'll be a log thing. So your answer will be 15 halves log 22, right? It'll have that kind of look to it. We go with that? Right. You didn't mind me picking you, Anna, did you?
No.
Good. I might do it again one day, or I might pick Eleanor next. Who knows? Just whatever we can get up to. Oh well. Question 11. You see the region R is now described in this one. So I'm always allowed in rectangular regions to decide X's or Y's first. And it depends on what this looks like. What do you think would be the best choice to make my life easiest? X's or Y's first?
Y's, personally.
I agree. What's your reasoning behind Y? That's the one I would have did first as well.
If we decide to do X, it's just going to be really ugly. I guess because there's only one Y in there.
Yeah, that would probably how my brain would have seen it. And I keep saying this because I don't want you to be too caught up on this if this part of what I'm doing doesn't gel with you. You know, it's okay to do X first and then do Y. You're going to get the right answer, right? If you do the math, you're going to get the right answer. It's not like, oh, I did it the wrong order, so now the question's wrong. No, it's the right answer. If you've got an expression and there's a heck of a lot of X's and only one or maybe two places where a Y is, a heck of a lot less, I would tend to go for the variable that's got less first. Because with a bit of luck, not all the time, with a bit of luck, it might make the X's a little bit easier later on. Because when you do the last one, aren't you just doing X's? So it's a Calc 2 question. And it's a little bit easier to deal with a Calc 2 question because you know how to do Calc 2, right? Integrals. So in this case, we're going to do the Y's first. And we have 8x. So I'm just writing this at the side. This is kind of what my brain is thinking. And we're going to integrate it with respect to y. And if you don't like that, kind of think to yourself, what would I have done if all the x's were just random numbers like 42 and whatever? I'm just putting whatever digits I feel like, right? What would the integral of this be? Don't need the specifics, but what would it be roughly?
ln of 1 plus 3y.
Okay, so it's going to be ln of 1 plus xy. Now, what about the top? Wouldn't that get you 42? So won't you just have 8x of ln of 1 plus xy? Right, so far so good. Right, the integral of this, the 8x stays put because 8 is just like a number, right? This gives you a log. Oh, wait a minute. If it was 1 plus 2y, wouldn't you get times a half? And if it was 1 plus 42y,
exactly.
you'd get. So you're going to have something else, aren't you? Times
1 over x.
And then you say,
Right.
hey,
Yeah.
I just get an 8. I'm not saying that's going to happen every time, but, you know, take what they give you. So it's now going to be the integral from 0 to 8 of 8 log of this guy. So what do you get? You get 8 times the natural log of 1 plus x times 1. Take away 8 times the natural log of 1 plus 0 times x, which is just 1. But wait a minute, isn't 8 log 1 just 0? So what we really get is the integral from 0 to 8 of 8 natural logs of 1 plus x dx. How do you find, I know this says 1 plus x, but how do you find just the natural log of x, which is a simpler version of it? What technique would you use to find the natural log of x?
Integration by parts.
Yeah, if you did, you would eventually get x log x plus x.
Yeah.
Now, it's not log x, it's 8 of them. Well, what will that get me? It will get me 8 lots of this guy. But it's not x, it's 1 plus x. So it will give me 8 lots of that guy. So it's going to be 8 lots of x log x plus x evaluated at x equals 0 and